Hello everyone, let's look over chapter 21, part 2. The aldol condensations. When an aldol product is heated under acidic or the basic conditions, the alpha beta unsaturated carbonyl forms. This is the aldol condensations. Aldol condensation occurs when an aldol addition is performed at elevated temperatures. So we can get alpha beta unsaturated carbonic compound. We look at the aldol addition mechanism. Part 1, the alpha position is deprotonate to form enolate. Enolate serves as a nucleophile attack on aldehyde, and after proton transfer spur, you can get aldol addition product. Part 2, elimination of water. The alpha position is deprotonated to form enolate. So proton transfer step to generate cup anion. Hydroxide is ejected to avoid aldol condensation product. When two stereoisomeric pi bonds can be formed, the product with fewer steric interaction is a major product. So this is a E form, this is a G form. E configuration product is a major, G configuration is minor. So you can see steric hindrance in this product. So because aldol condensation is favored, often it is impossible to isolate aldol addition product. This is aldol addition product, and this is aldol condensation product. It's how to isolate aldol addition product. The yield for condensation are typically much greater than yield for addition reaction. When you use cyclohexanone and sodium hydroxide at 100 degrees Celsius, we can get 90% of aldol condensation product. When you use 10 degrees Celsius, when you use cyclohexanone and sodium hydroxide at 10 degrees Celsius, you can get 20% of aldol reaction product. Two different aldehyde ketone react in cross aldol reaction. You can see two different aldehyde to generate four possible aldol product. So this is aldehyde. So two more of aldehyde to give aldol addition product. The other one, two more of aldehyde gives second aldol addition product. Cross-aldol reactions are only practical if number of products can be minimized, which is achieved in one of the two ways. Number one, only one of the substrates is relatively unhindered and without alpha proton. So there's no alpha proton here. So you can get cyclochloride aldol reaction. Also, benzaldehyde, there's no alpha proton. So you can get crossed alkyl reactions. So number two, use lithium diisopropyl amide as a base. So acetone liquid lithium diisopropyl amide to generate enolate ion. Enolate ion liquid aldehyde to generate directed alkyl addition product. So intramolecular alkyl reactions form cyclic compound. One group forms enolate. This part attack the other side. That's the groups. So only 5 and 6 members of the ring form well this way. So in this case, we can see 5 members of the ring form. Ester also undergo reversible condensation reaction. This type of reaction is called Claisen condensation. So this is Claisen condensation products. So alpha, beta, keto, ester. This is alpha, beta, keto, ester. Claisen condensation is simply nucleophilic acid substitution reaction. Nucleophile is enolate of the ester. Electrophile is ester. When you look over the mechanisms, the proton transfer step, nucleophilic attack to carbon-carbon, loss of leaving group. After proton transfer step, you can generate stabilized enolate. So last step drives the reaction to completion. So we need acid workup to obtain the neutral products. So after proton transfer step, we can get product. There are some limitations to Claisen condensation. Number one, starting ester must have two alpha protons because removal of the second proton by alkoxy ion is what drives equilibrium forward. Number two, hydroxide cannot be used as a base to promote Claisen condensation, otherwise ester hydrolysis occurs. Number three, alkoxide matches Y group of ester is needed. Otherwise, trans acidifications occurs. So now you can see methoxide attack to carbon and remove ethoxide. So we can get trans acidification product. Closed Claisen condensation are only useful if one of the following criteria is met. Number one ester has no alpha proton. In this case, there's no alpha proton. Number two, perform dielectric Claisen condensation with lithium diisopropyl amide as your base. When you use lithium diisopropyl amide with ester, you can generate enolate ion. And you could attack to carbon, you can get product. Intramolecular collagen condensation can be also achieved, called Dingman cyclization. So when you label numbers 1, 2, 3, 4, 5, 6, so there are two steps. Use base and next acidic workup. The deprotonation step and nucleophilic attack to carbon to generate 5-membered ring. The Engman cyclization prefer formation of 5 and 6-membered ring. In this case, 5-membered ring. Alpha position can be alkylated when enolate is treated with alkyl halide. So there are two steps. Step 1, use base. Step 2, alkyl halide. Then you can generate alkylation of alpha position. The enolate attacks alkyl halide via SN2 reaction. The typical SN2 reaction apply when secondary or tertiary alkyl halides are used. E2 elimination dominates. Alkyl reaction also compete with desired alkylation. So strong base such as lithium diphosphate amide must be used. Residual selectivity is an issue with unsymmetrical ketones. So two different enolates can form. For example, when you use base, you can generate thermodynamic enolate. So now on CC double bond, you can see 1, 2, 3, 4 substitute. On the right side, you can see kinetic enolate. So 1, 2, 3. There are 3 substitute on CC double bond. So less stable but forms faster. This is more stable enolate. So kinetic enolate is less stable enolate. Thermodynamic enolate is more stable. Kinetic enolate favored by irreversible condition. You can use lithium isopropyl amide at low temperature. You can use sodium hydride at room temperature to get thermodynamic enolate. So this is thermodynamic enolate. This is kinetic enolate product. So malonic ester synthesis, alkyl halide, is converted into carboxylic acid with 2 additional carbons. So 1 and 2 additional carbons. Diethyl malonate. Diethyl malonate is starting molecules. It is first react with the base to form corresponding enolate ion. This enolate is linked with alkyl halide. Both ester groups are hydrolyzed. Ester groups 1 and 2. When you use acid worker, we can get carboxylic acid. One of the resulting carboxylic acid group is decarboxylated with heat. So you can cleave this part decarboxylated with heat. So 1,3-dicarboxylic acid. So 1, 2, 3. 1,3-dicarboxylic acid undergo decarboxylation. So rearrangement and tautomerization, you can get product. So dialkylation, malloying ester synthesis overalls. There are 3 steps. 1, 2 step to generate product here. And diethyl malonate can be dialkylated. So there are 2 steps to get alkylated product, and then also you can use base and alkyl again to generate dialkylate product. And acid worker at high temperature, you can get dialkylate product. So acetoacetic ester synthesis analogous to malonate synthesis. So convert alkyl halide to methyl ketone with 3 new carbon atoms. 1, 2, 1, 2, 3. 1, 2, 3. So alpha beta unsaturated carbonyl. Alpha beta unsaturated carbonyl made by beer aldol condensation. The alpha beta unsaturated carbonyl have 3 resonance contributors. Electron movement to generate carbocation oxo anion. Then movement, you can see carbo secondary allelic carbocation. So beta carbon and carbonyl carbon are electrophilic. So carbonyl carbon, the beta carbon electrophilic. So either carbon can be attacked, depends on nucleophile used. So Grignard reagent generally attack carbonyl position. So this is called 1-2 addition. 1, 2, 3, 4. 1-2 addition, you can get 1-2 addition product. The Gilman reagent generally attack beta position. This is called 1-4 addition or conjugate addition. When you use Gilman reagents, second step, hydrogen ion, you can get 1-4 addition product. The mechanism of conjugate addition. So 1-4 addition and rearrangement to generate enolate ion. And proton transfer step, you can get enol. So the enol tautomerizes to the aldehyde or ketone. Aldehyde or ketone. So base, deprotonate, and rearrangement, so you can get product. Stronger nucleophile tends toward 1-2 addition. The less reactive nucleophile tends to conjugate addition. So typical enolase gives a mixture of 1-2 and 1-4 addition product. Stabilized enolate, this one, gives 1-4 addition It's group 3. So 1, 2, 3, 4. Micro addition on here. And then proton transfer step, you can get product. This conjugate addition, one-for addition, is called microreaction. Microdonor is nucleophile, thus conjugate addition. Microacceptor is alpha-beta unsaturated carbonyl. This is microacceptor. This is microdonors. When you look at the table, you can see a list common microdonors and microacceptor. On the left side, you can see microdonors. And then on the right side, you can see microacceptor delta positive. So Gilbert Stock developed synthesis using an enamine intermediate. So recall how an enamine is made. Cyclohexanone with 1 and 2 secondary amine. In the presence of acid, you can generate an amine. So enamine behave like enolate. They are nucleophile. They are nucleophile. But enamine is less nucleophilic. Enamine is microdonor. After conjugate addition, aqueous acid convert both group into carbonyl group. So this one into carbonyl group. So overall three-part process is stock enamine synthesis. Number 1, formation of enamine. Number 2, micro addition. Number 3, hydrolysis to get product. Robinson annulation is two-step process for forming a ring, especially micro addition followed by intramolecular aldol condensation. Thank you for watching video.